All right, hello. Welcome to Dr. Taylor's Calculus Lessons. This is for anyone. I'm going to be very general and give lessons throughout the sections of calculus that will be covered in an AP Calc course, AB, maybe BC. And I just want to dedicate this to the group that I'm doing it for, and it'll be continued in perpetuity for everyone, but Carnahan, class of 2015-16, AP Calculus. This is for you and for everyone else who comes after you. All right, let's get started. First thing I want to say is we're going to talk about limits today. And what limits are is they are simply something that a graphical output value approaches. All right? And that might seem weird to hear right now, but it's not bad, and as you will see, it's very, very understandable. Okay, so let's go ahead, and even though we're in this calculus activity, here's a do now. All right? And we're going to look at three different expressions. The reason we're doing a do now on this is so that we can remind ourselves about domain and range. Domain is the available values that you can use as an input into a functional relationship. A range is the output values that I will achieve by putting in the input values. The range is what I'm assessing when I look at the limits, the output. All right? But it's important that I understand what values I am able to input by understanding what's called domain restrictions. So, let's look at these individually. We're going to focus mostly on the domain. So this first one is x plus 1 over the quantity x times the parenthetical statement x plus 4. Okay? And if we're going to look at the domain, what we're going to look for is what values can't work. I mean, there's probably a multiplicity, maybe an infinite number, really, if you think about it, of values that can work. But what can't work? So we're looking for the counterexamples, the domain restrictions. So I'm going to focus on the bottom, because if I have a fraction, there's one value I can't have on the bottom of a fraction. Think about it. That's right. It is 0, because I can't have sum of nothing. I can't have a part of nothing. Nothing is sort of conceptual, right? So we can talk about what that number over 0 means as we go on here, but right now we're going to use the term you probably learned in algebra called undefined. Undefined means I can't define it. That means I can't find the place on the number line to put the dot. That's what undefined means. Where do I put the dot? I don't know. It's undefined. Okay? So we're going to focus on what makes the bottom undefined, because that's going to give us our domain restrictions. So let's look at this. X times x plus 4. Well, clearly, if I wanted to make that bottom equal to 0, I would set it up like such. Now I'm going to say not equal to 0, because that's what can't happen. But you could think of it as equal to 0, solve for it, and then those are the things that can't be done. It's not that important as long as you understand what you're doing. I'm going to put not equal to 0 right now up front, because if you don't understand what you're doing, it's telling you this can't happen. Okay? All right. So look, if some number times another number equals 0, you should know the multiplicative property of 0. And what does that mean? That means if I have this times that equals 0, either this is the 0 or that is the 0. And possibly this and that could be the 0 as well. But at least one of them have to be a 0 in that product. So one of the factors in the product must be a 0 to have a 0 output. It just has to be. So if I look at this, I break it apart. Just like I said, either this is the 0, or in this case cannot be, or this is the 0, or in this case cannot be. And you solve, well, that one's done, right? X can't be 0. That's one domain restriction. X cannot be 0. Anything else is cool, except when we look over here. If we solve for x plus 4 cannot equal 0, we treat it just like an equality. I'm going to do the inverse operation. The inverse of addition is subtraction. I'm going to do it to both sides. So using additive property of equality, I'm adding a -4, which is just what subtraction is. All right? So when I do that -4 on both sides, now I have my domain restrictions. X cannot be 0, and X cannot be -4. Okay? So let's look on, and, oh, before we look on, how do I write that? This is what's called interval notation. All right? So I can have anything from -infinity, and that's what these parentheses means. If I had a square bracket, that would mean inclusive. You know, I'm saying, so this is open-ended, not a solid dot on the number line. So how come it stopped at -4? Well, should it have stopped at -4? That's a good question, I think, right? So let's see what we did. Aha! Because I had to jump over -4. Because -4 was not allowed. And this little U that I put in that place connects this piece to that piece. It means union, right? And so you can easily think of it this way. Wherever my domain restriction, here I have 2 domain restrictions, I'm going to have 2 U's, 2 union signs. Because I'm going to have to jump over this one, I'm going to eventually have to jump over that one. And that's why it's not inclusive. I can't include -4 because I can't have a -4. It would give me an undefined value. So what do you think is going to go beyond that? I went from -4 to the 0 as I'm moving left to right on the number line. I'm going to jump over the 0 with a union sign, and I'm going to go from 0 to positive infinity. And because infinity isn't a value you can put a dot on, it gets the open ends as well. So this is the limits. The limits are whatever the output is whenever I plug in these values, okay? So we're not going to focus too much on the range. We're going to focus on the domain, as I said, and the range will be the outputs that we analyze as limits here shortly. So let's do this one. I'm going to have you think about what you got to do. I'll give you a hint. I'm going to set both of these things equal to 0, or in this case, not equal to 0. Now, you stop the tape for a second and solve it. Okay, if you didn't stop the tape, oh well. But if you did, here we are again, and I'll go over it with you. So, noticing that when I add 1 to both sides, I'm not going to belabor the Algebra 1 much here in AP Calculus class. I'm going to get an x equals 1, or in this case, does not equal 1. If I add a -2 or subtract 2 from both sides, I'm going to get x is not equal to -2. So I have, again, from infinity to -2, because when I'm moving left to right, I get to -2 before I get to 1. It's convention, right? I think it's an important way to do it. It makes the most sense. So then I'm going to need a union that jumps over -2, but connects me to the next piece, this and that. That's what the union means, okay? Well, when I'm combining them all together, in this case, we can nuance those and or statements when we're doing set theory. But right now, this is saying this piece and the piece that goes on to infinity. Not including -2, not including +1. Okay? Here's one. What's different about this one? Think about it. Can you factor a trinomial? Okay? Now these are very artificial questions. We know in the real world these beautiful trinomials that factor into 2 wonderful binomials with nice integer values, that's all artificial. It's meant to get you used to looking for conditions and patterns of factorability and cancellation and what have you. But in the end, in the real world, these numbers always, almost always, never say always and never say never, right? So these are generally, most of the time, not going to end up factoring into beautiful things. But in this case, it does. So I'm going to break that thing into a factor. And real quickly, how you factor that is you look at what multiplies to be a 2 and what either adds or subtracts to be a 3. Well, clearly 2 times 1 is the only factors available to multiply to be a 2. We're talking about integer factors now. So 2 and 1 make a 3, that would be addition, right? And since that's positive, I want to same sign value for multiplying, and since that's positive, both signs must be plus to get me to 3. Otherwise, I'd be doing some subtraction, and I'd end up with something less than 2. So that's that's the overall strategy. Use that method we've talked about before, where we made the list of possible factors, add and subtracted them all, or you can use that algorithmic list I just articulated. So that cannot be. I set it up to be two binomials. I know x times x is x squared. I know that 2 times 1 makes it 2. I don't know whether it's add or subtract. This is the method we did in Algebra 2. So I said, let's try both and see which one gives us a 3. That one does. And then we look at what kind of 3 we want and see what kind of 3 did we get. If they align, then these numbers with their signs as is go. If they don't align, then I take the opposite of everything, and those signs would change to their opposite, but then they go over. So in this case, we can take it as is, and we can put them right in there. And now, we're back to this times that equals 0, which you can solve. Do it now. Okay, welcome back. And anytime I ask you to do it now or what have you, that's your cue to pause, and I'll wait a couple of seconds so you can get to the pause button. All right, so there we go. X plus 2 is not equal to 0, so x is not equal to 2 because negative 2 and 2 make 0. The logic of it is negative 1 and 1 make 0, so x cannot be negative 1. The logic of it is pretty straightforward when you use English words. Okay? So there's my interval up to negative 2. My union at negative 2 jumps me over from negative 2 to negative 1. My union at negative 1 jumps me over from negative 1 to infinity. That's my domain, right? That's what the D stands for. Any of these things works, but not all real numbers. All right. So now, what the heck is a limit? There's a couple ways we're going to look at it. Your book does 1.2, and your current book does finding limits graphically and numerically. I'm going to go right to looking at an equation and thinking about its limit, and at the end, I'll add on how do I look at it graphically. It's really quite simple. But let's talk about this notation. The limit as x approaches a of the function f, whose input is x, which is important, right, equals some value we're going to call L, and I guess you can tell that that's for the limit value. All right? And what this means is x approaches a, the function approaches some x output value, I should say, that is discrete. I can put my finger on it. I could put a dot and a number line on that value. Even if the function didn't reach it, I could define it. That's what it says. Okay? So, this is my output. Why? Because that's f of x equals, you might say x squared plus 2, right? You'd say y equals mx plus b, right? I could say f of x equals mx plus b. In other words, that's the output part. This is the output. This is the name of the function, function f, with the input variable defined. It is not f times f. It's f of x, f evaluated at whatever I put in for x. That's what it's about. Okay? Next, I look at this. This says the actual value of the output at the input I am approaching a. In other words, if I put this value in, if that was 2, and I put 2 in and I could then solve with the 2 in the equation, it would give me a number, and that would be my limit. It's really, really simple. It's almost like what you've been doing all along, going back to Algebra 1 when you just plugged in values for x and y and see what the expression evaluated to. It's much like that. All right? So, and sorry I keep hitting the wrong arrow. Now, this is read as the limit, L-I-M, the limit as the input approaches a, or the limit as x approaches a of the function f is whatever. Okay? So now, that was for a few years ago when we were using Stewart, so that's not important, but it does tell you where these lessons, these examples are coming from. So those books are somewhere in the building. You're not using that Stewart book anymore. You're using Calculus of a Single Variable, edition 10 from Larson. And I have on my website, math-science.weebly.com. You go there, you go to the left, there's a left menu bar, you hover over class pages. Out will slide Unit 1 from every class I taught while I was at Carnahan. you'll click on you'll click on AP Calculus, and it'll take you to Unit 1. As soon as you get there at the top, you'll see Unit 1, Unit 2, Unit 3, Unit 4. You're going to click Unit 2. Unit 1 was a review unit. Unit 2 is where we're at. Okay? So I'm going to write that here. Math. And these aren't all caps. You know that's just how I write. Dash science, not underscore, dash, dot weebly.com. Okay? Over on the left, you hover over class, pages. Out will slide some pages. You're going to click on AP Calc Unit 1. And after you get there, you're going to click on Unit 2 in the top bar. It'll be Unit 1, Unit 2, Unit 3. Okay? All right, let's move on. So here's a problem. The limit as x approaches 2 of this function, that will be the function f of x. You see it? That's function f right there. What's the input value, or variable, I should say? Well, it's x. See it? And this is saying, let that input be 2. That will be the limit as x approaches 2 of f of 2 equals, that would be how you might read that. It's very straightforward. So what do? I simply plug in a 2 everywhere, right? So if I were to plug in a 2 everywhere, what happened? Sorry. Board's a little bit wonky for me. You know, the best part about this is it's on tape, and I made that mistake, so there you go. Imperfection from the get-go. It's okay. No one's perfect. Your answers are wrong more than they're right. Wrong things lead you to right conclusions. When you work together, every voice is important. Remember that. Nothing is stupid. Everything leads us to a better conclusion as a group. Your collaborative understanding will develop your sense of knowing when you're right without having me in the room to ask, because I'm not there. Okay? But you can together collaborate and come to consensus. And some things you can check in the back of the book. There's always that. Okay? So, what I was going to do was add a little extra step in here. Okay. So, what this is basically saying, so that you know what you're doing, is I'm taking this 2 and I'm plugging it in everywhere I see an x. And when I do that, I end up with 2 squared minus 2 plus 2. Well, obviously, negative 2 and positive 2, they're going to cancel one another out, leaving only 2 squared, which of course equals 4. So since this came to a discrete point and you could evaluate it, that's its limit. It not only approached it, it actually can land on it. And one of the ways you know that sometimes there's not going to be any limit value that I approach but don't actually reach is when this is not a fraction. Because I can put anything in there, right? There's no square roots, so I can put any negative sign in there. There's no fraction bar, so I can put anything, even a 0 in it. So because there's no square roots or there's no fraction bar, pretty much all real numbers are my domain. Which means I plug in what it says and I should get an output that's legitimate and actualized. Okay? Very straightforward. So what happens if this becomes a minus? You try it. Okay, welcome back. Now, this is simple as the last one. I put in a 2, and I get 2 squared, which is 4. I put in a 2 here, but that makes it negative. So I have a 4 minus 2 minus 2. Well, 2 negatives together make negative 4. Remember, I'm not multiplying. Don't do some silly algorithm rules. I'm borrowing $2 and borrowing 2 more. I owe $4. So there's the $4 I owe, and there's the 2 squared. There's the positive $4 I have. So if I have $4 and I owe $4, when I pay the person I owe back, how many dollars do I have? Of course, I have no dollars. You know? All right? Pretty straightforward again. I'm just plugging it in, and I know that that's not putting too much strain on any of you. what if, now this is just a what if, but what if this was 1 over that function? Then when I plug in 2, what would I get? I get 1 over 0. And what is that again? Oh yeah, undefined. I don't know where that lives on the number line. I know it's an output, but I don't know where on the y-axis to put the dot. Okay? So that's a problem.
Also, Holden, can I get my key?
I'm in a classroom.
Thank you.
I tried the weekend to avoid that, but nevertheless, here it is. C'est la vie. All right, so what would I do then? What's the limit? Is the limit 1 over 0? Absolutely not. Because that's undefined. I can't have an undefined limit. If the limit was undefined, there would be no limit. Just like if the limit was infinity, it just kept getting bigger and bigger forever but never stopped, then there's no limit. See, so the limit is what I'm approaching. If I'm not approaching something discretely, then no limit exists. So, no limit. All right? Now, let's take a look at this. I went back to change it a little bit to plus 2. Okay? So we're going to do the table method, because the table method is for when you can't just plug it in and get an easy answer, and you're not sure what it's approaching, and so you want to look at it from both sides. Remember when I'm inputting x values, if I go from left to right, my x values are going from negative toward positive, right? But I also could go from right to left. I could go from positive towards negative in my inputs. Now my output, it'll be wherever it is, but could I not start putting inputs in and approach it this way or that way to some common domain value that I say I can't define, but I would like to know what it would be approaching as an output? And yes, the answer is yes, I could. All right, so let's do the table method. And what the table method is I make a table, okay? And so I'm going to go 1, 1.5, 1.9, 1.99, 1.999. And what you'll find after you do this a few times is you can just start from like this point and get close, close, close. That's one side. Which side am I approaching my x value of 2 from? Am I approaching it from the left or the right? Well, if I think about a number line, 1 is on the left side of 2, isn't it? So I'm approaching this. So this is what's called the left limit. If a limit does exist, it is the same if I evaluate it as a left limit as it would be if I evaluate it as a right limit. Okay? So if that's the case, then we'll deal with that. Okay? But right now, let's look at the left limit. All right, so when I put 1 in, I'm going to get an output. When I put 1.5 in, I'm going to get another output. When I put 1.9 in and square it and subtract it from that, so that's going to be 1.9 squared, negative 1.92, so that's 1.9 squared plus, what, 0.1, right? So those values are doable on your calculator. I'm not going to belabor that on tape, all right? Also, I want to approach from the other side. So if I started at 3, right, and I approached 2, right? So basically I started at 1 and 3 and approached 2 from both sides. Again, 3, 2.5, 2.1, 2.01, 2.00, 2.0001, right? Again, in reality, you could start at 1.9 and go 3, and at 2.1 and go 3. And if it's going to approach, you'll be able to tell. And a lot of times they converge, and sometimes they seem to be converging, but one side's positive, one side's negative. That's not convergence, that's divergence. So don't be fooled by the number, the signs matter too. So when we plug those numbers in, what we get, when we plug in 2.001, and we keep going, going, going. So right there we got to 4.003, right? And when I plug in 2.0001, I get to 4.0003. It's clear that that's approaching 4.000000 something, which we can round to 4. The same analysis could happen on this side. Okay? And when I do that, if I put in 1.999, I get 3.9970. So that's good. That's approaching 3.9999999, which is roundable to 4. Both of them are positive, and we know that 4 is the output because we plugged it in, didn't we? So what we've done is proven the table method is usable at any time, and it will give us valid answers by that one example, but you won't find a counterexample. This table method works. You can search for it, great exploration in mathematics. All right. So we can see that I've approached 2 from the left, starting at 1, and I've approached 2 from the right, starting at 3, and I color-coded it. And since they converge at around 4, we can accept that our limit is 4. L equals 4 is how you write it. And that was my input that I was approaching. Are there any questions? That's a joke because I can't answer you. But there are always the times we can get together and the email questions, we can Skype, or you can video some questions and save them and send them to me, all right, submit them to me. And we can also share a Dropbox so that you can put videos onto the Dropbox and I can view them that way. We don't all have to share the videos to me. You can do them as a group. We'll talk about that, okay? All right, well, what about a piecewise function? And you're like, what? Probably don't remember those. But if you remember, a piecewise function is a function whose domain restrictions change throughout the course of all the functions. So in other words, this is saying that f of x is not defined by one function. It's defined in pieces, and each piece has its own functional expression. So f of x is a fraction, x minus 1 over x squared minus 1, if x does not equal 1. And that's simply any number except 1, even 0.9999999 and 1.00001, right? I mean, just like we checked with the table method. But if x equals 1, then it's 2. So in other words, all real numbers except 1 here, and here nothing except 1 works. That's what this is saying. It's defining them. If x is this, if x is that. F of x is 2 if the input is 1. F of x is this if the input is anything except 1. So there's 2 pieces. One of them is just a simple point, right? Input 1, output 2. That's 1, 2. I mean, I'm done there. That literally did itself. They aren't always that easy, but you can see what's happening. Here, I got to plug numbers in to get an output, but here they just gave me an output. If x is 1, your output's 2, don't even calculate it. So let's look at what that means. What that means is, if I did this graphing and I got some shape, okay, all right, then when I wanted to put in 1, right, if I put 1 in here and I did the math, I'd find the limit it approached, right? Would I? Let's see. 1 minus 1 is 0. 1 squared is 1 minus 0 over 0. Oh crap, that's not just undefined, that's what's called indeterminate. We can't even determine what 0 divided by 0 is. What's nothing divided by nothing? Is it something? Because if it's not something, I can't locate it in a number line. But if it's nothing, I know where that lives. It lives at the 0. It's neither something nor nothing. It's something we can't even determine. All right? Undefined means we can figure out what it is, but we just can't put a dot there. Indeterminate means we don't even know what it is. And that's what 0 divided by 0 is. Of course, 0 divided by itself is the only time that you don't divide a number by itself and get 1. And clearly, if you divided 0 by itself and got 1, that would wreak havoc on the banking system. I've got no money. I divide my account by 0, now I got $1 and I can start fresh. No, doesn't work that way. Okay? All right, so this is the general shape. And by table method, we can figure out where that approaches. And so it approaches at 1/2. So at 1/1/2 lives a hole. There's a hole in that function. But we are told, though, by this, that at 1, the output's 2. So there's a hole there with a dot. And that would be how that would show. Okay? So the 2 is not the limit, is it? Because as I approach to the left, from the left, am I approaching 2? No, I'm approaching 1/2. As I approach from the right, am I approaching 2? No, I'm approaching 1/2. So even though I have a discrete value defined there, it is not in the smooth, continuous piece of the curve. I'm going, and then I jump back down. So that jump isn't expressed as an approaching value. That jump seems to come out of nowhere, where I would expect that output to be 1/1/2. That's what I would expect, and that's why the limit is 1/2 and not 1, or 2, I should say. Okay? Very important, very important. All right, now, limit of sign. Now, I don't know why this says piecewise functions. Now it should say trig functions, right? So let's think about what sine looks like. Let me look at what my output does. Okay, it does. All right. So sine looks like a shape. If you remember cutting those triangles out and plotting the lengths, you remember that we had a green curve and a pink or red curve, right? And the green curve started 0, 0, went upward first. It looked like a sideways S, where the red curve started at 0, 1 and went downward first, and it looked like a curvy U or V. So, but we know that if we kept going in both cases, it's really a wave function, which we call the sinusoidal function. It just, sine starts at a different place than cosine does as far as where it crosses the x-axis. So, the limit as x approaches 0, I can do that as sine of 0. You could do it in your calculator, and when you do, you get an output of 0. We're going to look at the graph shape and figure out why. Knowing those graph shapes is important because you can think through the problem without grabbing your machine. Your machine is there to compute things that are tedious, not to give you knowledge you should have within your head from trial and practice and what have you. It can fill in the knowledge holes, but you want those to be there so you can think critically without relying on your robotic device. Okay? It's a tool, not a crutch. As long as you remember that, it's beautiful. All right. But when I put a 0 at the bottom, what happens? Undefined happens, which means no limit, right? So let's take a look at that. When I plug in 0, that's what we just talked about, I get that problem right there. So when I think about where 0 is on sine, when I'm at 0, since sine starts at 0, 0, the output 0, so this is basically 0 over 0, which is that indeterminate value. You remember that? Indeterminate, not undefined. That doesn't mean I'm done. That means I check it with a table. If the table doesn't give me a value, it's no limit. But I can't just say, oh, no limit, because I haven't checked it with a table. The table is my last resort. And it's the most tedious, but it's also the most critical. When you skip it, you've blown it. And so don't skip it. So let's look at our table. Let's approach 0. I got 1, 0.5, 0.1, 0.00. So I could approach it from anywhere. But when I put in 1, and I put in -1, look at my values. Notice that they're the same. One's not positive and one's not negative. That's encouraging to me. Now they might bounce back and forth, so I need a few more problems. I need to know what the pattern is. That's why I don't just do this one and that one first. I got to do a few to see if there's a pattern that I'm ignoring by just focusing on really, really close to my limit value and shortcutting myself. So the next one, I figure, well, let's jump a little bit because that was encouraging. And I jumped to 0.01 and to -0.01, and boom, look at that. So what do they look like they're approaching to you? From 0.84, you can think of it as percentages. From 84% to 99.9%, But percentages stop at 1, and this might go over 1. But the notion is percentages are easy to think about. When I see decimals, I sometimes think about them as percentages, and I can relate to them a little easier as how they compare to one another. Because we're used to thinking about our test scores, right? All right, so I put in another one, 0.001 and -0.001, and look at that. So it's clearly approaching the value 1. So if we think about it as graphing, right? I could graph those values. What's going to happen is I'm going to have a line on both sides, but at that value, it really doesn't exist. We said it should be 1, and notice from the left it approaches 1, and from the right it approaches 1, but at 1 there's a hole. There's a hole because it's indeterminate or undefined, whichever one it was. It doesn't really exist, but it's getting closer and closer to that. That's what a limit is. It's a theoretical value that may or may not ever be reached. And in this case, it's never reached. It's approached and approached. Kind of like an asymptote. If you remember an asymptote from secant and cosecant, I'm approaching it, or tangent or cotangent. I'm approaching the asymptote, but I'm never crossing it because I can't get a value at that asymptote. That value is undefined. Okay? So, piecewise function, real quickly to close this out. This homework that's up there, that's in the book, the Stewart book. That's no good. The Larson book has homework. what I can do is we do the email thing. I'll give you, and you get that with Coop as well, I'll give you problems from your book. I think you should be doing that way. You can work out of your book. But if you work out of the Larson book from the website, on my website is the answer key to Larson's. Not this, the answer key, the solutions manual for all the odds so you can see the steps. So it might be nice to do homework from the Larson book, the blue, older Larson's book that's in the bottom of my big file cabinet up in the front corner here, and do those assignments, do the homework there, and you can play around in the Stewart book as well, or the new Larson book as well, but the old Larson book, I have the solutions manual online for you so you can get to it. And that's a real handy thing to have when there's no one in the room to work it with you, okay? So if I approach from the left, so that's what that little sign above the 3. It's not 3 with a negative charge like you think of in chemistry. And it's not -3 because that would be negative in front. This is 3 with a negative sign, means I'm approaching from the lesser side of 0. I'm approaching from negative side. I'm approaching from the left. So obviously if I'm approaching from the right, that symbol would be plus. Okay? So approaching from the left, as I get closer to 3, I'm approaching, 1, 2, 3, 4. I'm approaching an output of 4. But notice on this function, there's an open hole at 3, 4. What does that mean? That means it doesn't exist there. That means if I had the piecewise function, it would have f of x equals, and there'd be 3. One function to represent this, one function that represents that, and each of these with their own domain restrictions, and one function that represents that. So now, if I look at x 0, right, as this function approaches 0, would there be a limit? Absolutely. What would it be? It would be 3. But as that function approached 3, that was not the limit. So you can have a piecewise function where your limit exists, and you can have a piecewise function where your limit doesn't exist. You just got to be careful and make sure you're paying attention to your domain restrictions and what x is approaching in your limit statement. Very important. Those two go together, inextricably, and that's why we had the little do now section. All right? So approaching from the left. Now if I'm approaching the limit of 3, right? So as x approaches 3 from the left, it's 4, right? Doesn't it really exist? It's not 4, but it's approaching 4 from the left. Oops. Well, that was it. Well, what if I was approaching from the right? Let's do that. Theoretically. If I'm approaching from the right, so this would be the limit as x approaches 3 with the plus sign, would that still be 4? Clearly it wouldn't. It would be 2, wouldn't it? So if I approach from the left and it's 4, and I approach from the right, it's 2. Do I have a limit? I have a left limit, yes. I have a right limit, yes. But if those limits aren't the same, then I don't have a limit. And the answer would be no limit exists. All right, so that's the basics of what a limit is. If you go to my website, you'll find there is a calculus help little link on the right-hand side, which is a wonderful little short, cartoony kind of thing. Great. It's great, all right? And he has a number of them. You look at them all, one by one. All right, this closes the lesson. Thank you very much.